Okay, today this is makeup. This is a class for September 6th, Tuesday. So in section 4, we're gonna start study the observed information. So the observed is the okay, in the missing data setup, we have observed likelihood. So from the observed likelihood, we can derive observed score function, which is this one, and then take the partial derivative again to obtain the Hessian, negative Hessian, which is the Fisher information, which is this one. And then if you take the expectation, this is a function of parameter only, right? That is called expected Fisher information. And then this theorem is essentially missing data version of Bartlett theorem, Bartlett identity. So the score function has zero expectation, and variance of the score function is equal to the information matrix, observed information matrix. I mean the expected information matrix. So we are now interested in estimating computing the MLE, and then we know that the MLE should be the maximizer of the observed likelihood, right? So at the head is the maximizer of the observed likelihood. So which can be obtained by solving this score equation. And then usually we take the Taylor expansion. So we know that is at the head MLE supposed to satisfy this equation. So then we can take the Taylor expansion around the true value. Right, at the head minus at the 0, and then from there we can compute the expected. So that's very similar to what we did for MLE, asymptotic normality on the no missing data. So that is basically the same structure. And so this observed score, so expect Fisher information derived from the observed likelihood need some more discussion. So here's some comment. So decomposition of the information matrix. So remember, this is a conditional, right? So conditional description of missing data given the observation. So this conditional expectation is joint distribution, right? So that is the Y obvious, Y miss. Okay, something's not okay. I think it's okay. So let me somehow I couldn't share it. So let me share it again. Okay, yeah. So this is conditional, and then we need the joint divided by marginal, right? So marginal. So marginal is okay. Joint divided by marginal. So we have eta here, if you want. So conditional equal joint divided by marginal. And then let's take the log. So then log of y is given. Okay, let's write it. So this is the conditional distribution. And then this is a score function associated with this conditional distribution. That means this is the definition of as miss is log of the conditional score, conditional distribution, right? Let me write it here. So let's use this space. Okay. So S miss eta is a score function from the conditional distribution. That is sometimes called prediction model for missing data. So log of the prediction model of the missing data given observed and delta. Okay. And then we now take the joint and marginal. Right? So, and then this is called as com data because it's a complete data. And this is called as miss observed because it's based on because it's a score function derived from the marginal distribution, right? Observed data. So that is this one. Okay. And then if you take the, so that is actually, we already discussed this before, but let's just do it again. Right? If you take the conditional, so that is the definition of this guy is as miss eta f y miss given y obvious delta eta d mu y miss, right? So this guy is 0 by Bartlett because by definition this score function is a partial derivative of the this density function, log partial derivative of the log of this density function. So that is what Bartlett identity is about. So now we know this is S com eta minus S obvious eta, right? And then that implies S com eta given y obvious delta eta is S obvious eta. So this is actually what? This is sometimes we call the mean score function. So that this is actually, the Fisher's mean score theorem, right? So mean score theorem. So we just reviewing the mean score theorem. Then that is this one. Okay. Identity. Okay. And now another interesting part is that these two are orthogonal. So if these two are orthogonal, then remember S-com is S obvious plus S miss, right? And then variance of this, so variance of the whole thing is variance of this and variance of this, and then covariance, 2 times covariance. And this 2 times covariance is here, which is 0. So then we have some kind of Pythagorean theorem. So then question is, so how to show this? Show equation 1. Use up the space. So let me use the space again. Okay, so question is covariance S obvious eta S miss eta. Okay, and first this is a vector, p times 1 vector. This is also p times 1 vector. So variance covariance matrix of the random vector, essentially, right? So then this is S obvious eta times S miss eta transpose, because then it's a p times 1 and 1 times p, so that it becomes a p times p, right? Minus expectation of the S obvious eta and S miss eta transpose. And then this guy is 0, right? That is a theorem 2.6. We know that this essentially Bartlett identity. We know the scope function has a 0 expectation. So then we have only to worry about the first term. And now what it can use is that, let's use conditional. Transpose given y obvious delta. Okay, it's a product. So then you can see that conditional on this is constant with respect to, that is of to y obvious and delta. So conditional on this, that nothing random. So then it can go outside the integration, I mean the expectation. And then the only thing left inside is this guy, given y obvious delta. This is 0. That's what we studied here, right? This guy. Okay. Okay. So that means the whole thing is 0. So that is the proof of the equation 1. So basically see, this is the original scope function, and S obvious, right? S obvious is a kind of projection, and this is more like a residual. So you can obtain some kind of anobody composition, because this is a sum of, so okay. My point is that you can view this guy as a variance of the expectation of S, given y observed and delta. And then this guy is, right, expectation. So Well, okay, let's write this way. So this guy is a variance of the SCOM minus conditional expectation. I mean, conditional expectation that we have here. So this one is, so if you can see this is, if you write it as a y, we have a variance of the expectation of y given x, and then variance of the y given expectation x, or something like that. So the expression here it resembles this kind of decomposition, ANOVA decomposition. Okay. So that has a name, missing information principle. Basically, we get information has can be added up. So missing information is the complete sample information minus observed data information, and then meaning. So the information matrix, because this guy is equal to this guy is equal to this, and this guy is equal to this. Okay. So the information principle is nothing but the ANOVA decomposition of the scope function. Okay. So let's use this example 2.7 to understand, to illustrate the idea. So here's a bivalent normal distribution. We have originally bivalent normal distribution. We have 5 parameters, right? mu1, mu2, sigma 1, sigma 1, 2, sigma 2, 2. So 5 parameter is too much. So let's assume that this is known. So, and we'll just worry about these two as a known parameter. And then the density function. So joint density, remember that this is exponential. I mean, this is Gaussian, right? So then, so it's like this: y1 minus mu1, y2 minus mu2, sigma 1, sigma 1, 2, sigma 1, 2, sigma 2, 2, inverse. This is not really good color. So yeah, inverse, and then this vector, and then transpose, right? So this is 1.2, 2 times 2, 2 times 1. So that becomes a scalar matrix. Okay. So that is the density fx y1 y2 has this part inside the exponential function, and then we take the log and take the partial derivative, then we get this one as a scope function, and then we have a summation. Okay. So this is no, on the complete sample, scope function is straightforward, and then if you take the partial derivative with respect to mu, then you and then take the negative minus, then you get this one. So the information matrix for mu based on complete sample is just this one, which is makes sense, right? If you take the inverse, you get variance. So the variance of this, so not variance, I mean the variance of the MLE, variance of the MLE mu hat will be I mu inverse, which is 1 over n, sigma 1, 1, sigma 1, 2, sigma 2, 2, which is variance of the variance covariance matrix of the mu hat 1, covariance of mu hat 1, mu hat 2, and then variance of mu hat 2, something like that, right? This is matrix. Okay. Now, suppose that there are some missing values in y1 and y2, and the original sample is divided into 4 sets. H, K, L, M. So H, Y1 and Y2 respond, K, Y1 respond, because you have a four possible, right? Observed, 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 missing, missing, observed, missing, missing. So that's, we have four possible, partition, possible response pattern, so that we can partition the original sample into four sets. And then let's consider, we use the mean square theorem. The idea is use mean square theorem to compute the observed score function. So H set, no problem, right? We observe everything. So in the H set, we just have the we don't have any loss of information. And K set, we only observe Y1. So in the K set, we need to take the conditional expectation conditional on Y1, because in set K, Y1 is the only information, observed information. So then, so we now decompose the complete sample score function into n component, right? 1, 2 through n. And then, so this is the, each one has this form. And now you want to take the conditional expectation of this guy, conditional on Y1. So then it's just a linear function of Y1 and Y2. So we have a Y1, conditional on Y1, we don't have to take the expectation. Conditional on Y1, the second term, we need to take the conditional expectation, right? And then, okay. Let's, so how to compute, how to obtain this one? Well, first of all, you need to understand Y2 given Y1. Under the Gaussian normality you have. So you need to, so this is the basic property of the normal distribution, right? Okay. So then we take the minus. So then the whole thing, so let's call this left-hand side. Okay. So left-hand side equal to sigma 11, sigma 12, sigma 12, sigma 22 inverse. Okay. And then y1 I minus mu1. And then sigma 12, sigma 11, oops, divided by, right? And then it's mu1. Okay. But see, here, you can notice that you have the common. So it's the same thing. So actually you can write it as, if you want, you can write it as sigma 12, 11, sigma 12 times y1 I minus mu1 divided by sigma 11. Okay. And then this guy. So see, this is nothing but the first column. I mean, right? First column of this matrix. So then this guy will be this one. Because if you multiply, right? If you multiply you will get the first column. So you don't have to compute the inverse, matrix inverse, but you can just use some algebra to obtain the result. So anyway, this is what you get. So that means you have information in the first component, but not the second component. The same way, if you conditional on, so okay, so this guy is interesting because the variance of this guy will be sigma 1, 1. So we can use symmetry to conjecture that we can have this form. Because you can just take the role differently, right? So that's what we get. And then now from here, you can derive the information by taking the partial derivative of the scope function, right? This is your scope function. And then take the partial derivative with respect to parameter and take the negative that you get. So for K set, I mean H set, you get this one. K set, right? If you in the K set, you have only this term. So the information matrix will be this one, right? Because so how? Okay, so you have a sigma 1 1 inverse y1 minus mu 1 0. That is your scope function, and then you want to compute the partial derivative of the mu 1 and mu 2. So that is this guy. Okay, and then you same story, right? This guy will be same thing of this guy. Then that is this one. Okay, so the interpretation. So if you look at this information matrix, that is interesting. So in the set K, you have a full information. I mean set H, you have full information. Set K, you have information only the first, right? The first element, one element of the 2 by 2 matrix. So that means it doesn't give you this partial information, does not give you any information about y2, mu2, but give a full information about mu1. Yeah, so same story here. Okay, so let's do some matrix algebra to talk about further. So let's, to make life easy, let's assume that this is 0. Okay, so we have only this kind of data structure, monotone x and y. I'm sorry, y1, y2, y1, and y2 is a subset. Okay, so that is the H set and K set. That's it. And then how to, we are interested in evaluating the variance, MRE, variance of the MRE, which is the inverse matrix of the observed information. So then you get this from. And how to compute the inverse of this kind of matrix, where we can use some sort of the, so you have, this is, okay. This is A, right? And then, so this is A. So we have, we use this matrix algebra. Okay, that is the name, Woodbury matrix identity, and do some matrix algebra, and then C, B is 1 0. Okay, 1 0 1 0 1 0 1 0, and then C is what? This one. Okay, so you agree, you will see that this is, okay, this is A. This is A. This times, this is C, and then B is 1 0. Okay, and then to this algebra, you end up getting this result. So after some matrix algebra, you can obtain this. So what does that mean? Well, so if you look at the first element, so first element, you get what? 1 over nh and plus 1 over n minus 1 over nh. So you get sigma 1. So that is actually what? Well, you have MLE, so you have your MLE for x, I mean y1, it's just y bar n, right? And so that is no loss of information. You don't lose anything because you observe, right? You observe everything. You observe you have a full observation in y1, so you don't have any loss of information. So that's why you get a full information. So that's not really interesting part. Nothing to discuss further. But what is interesting is this part. So what would be so this is the variance covariance of the, right? This is the variance covariance of the MLE, and the variance covariance of the MLE for mu2. So variance of the MLE for mu2 can be written as this guy, right? So this guy, this one is 1 over nh sigma 22 plus 1 over n minus 1 over nh sigma 1 2 square divided by sigma 1 1. Okay. So that is actually what? That is sigma 2 times rho square correlation. So that gives this form, right? So you have a sigma 2 rho square 1 over n plus this. So you can see that this is actually variance to sum of square, variance of the sigma 1 1 beta 1 square, something like that. And then this one is residual error sum of square. So this one is variance of the y2 minus beta 1 y1, right? I mean, you need to, of course, you need to, but this is actually error part. So basically, there's some component fully explained by y1, which is sample size, effective sample size n, and then the error sum of square part, you have an effective sample size nh, which kind of makes sense because if you think of the if you use some sort of a regression relationship, so as long as you have some component explained by y1, you don't have any information. I mean, you don't lose any information for this. So in the extreme case, if the correlation is 1, if the correlation between y1 and y2 is 1, then what? Even though you don't observe y2, because you fully observe y1, and you know that its correlation is 1, you should fully recover the information, right? So that's why we get, if rho equal to 1, then the sample size, essentially effective sample size, is just the sigma, I mean sample size n. On the other hand, if the correlation is 0, right, y1 and y2 are completely independent, then this y1 information is not really helpful in predicting y2. So then you just have nh. So that is the basically idea behind all this. Okay, so let's have a break and then we'll continue.